So this is EE 619, lecture 19. So we had implemented a 4:1 MUX. So it's I1. So this was S1 bar, S0 bar, S1 bar, S0, S1, S0 bar, and S1 and S0. Now, to bring this output all the way to VDD, we used a restoring logic, which consisted of a circuit like this. Right? And then I had asked you the question, if we were implementing let's say a 16:1 MUX or an 8:1 MUX, then the number of transistors coming in series here is going to increase, which means when you model it, this is now becoming a higher order RC circuit like this. Right? For example, this could be RS1, RS0, but if you had more number of transistors in series, you would have RS2 associated capacitors, the next resistor here, etc. And then when you are calculating the resistance, when you are calculating the Elmore delay, you know that this is going to have a quadratic relationship with the number of stages that you are going to use, right? It's going to increase in terms of n square. So the question I had left you with is, what can you do to make sure that the delay from input to the output is minimum and it doesn't increase as you increase the number of inputs to the MUX? Any suggestions? Yeah, so this is a 4:1 MUX, right? Here you have two transistors in series. If I go to 8:1 MUX, you will have 3 in series, 16, 4 in series. So basically, as you are increasing the inputs to the MUX, the number of transistors coming in series is increasing and your delay is going to increase in terms of n square. Now I want to implement a MUX with large n, right? How can I implement it such that you don't have the number of transistors in series increase? So I create two 4:1 MUX and then connect their outputs. Is that the solution? Break this into multi-stages, right? That is a reasonable solution. Anything else? Why don't you draw it on the board? We can discuss it. Right? So the idea is to, instead of having a combination, a series combination of two transistors, you somehow want to put a single transistor here. Right? And now I simply have to generate the control signal for it. So the quickest way I can tell you is to simply use a decoder circuit. So you will have S1 and S0 as input, and you will have P0 to P3 as output. And depending on the value of S1 and S0, only one of these outputs will be high, right? Now, depending on how many inputs you have, so if you have 2 inputs, you will have 4 outputs, 3 inputs, 8 outputs, etc. And you can implement whatever logic needs to be implemented to achieve this action. So now the thing is, if you implement your decoder circuit using the differential cascade voltage switch logic, then you get both P0 and P0 bar. In which case, it's very easy to implement the same logic using transmission gates also. You have both the selection signal that you want to apply here as well as its complement. Okay. You can do that also, but DC-VSL will give you lesser delay from input to both the complementary. They come at the same time. Sorry? Why not? DC-VSL was not ratioed. Its steady state was settling down to 0 and VDD. Pseudo NMOS was ratioed. Yeah. So now all the logic, yeah. The only difference is now the delay from input to the output is much lesser. So if you had I1 here, earlier I1 is going through 2 switches and reaching the output, right? So now if the selection signal was already on, the delay from input to the output is going to be much lesser. And this sort of implementation is more useful when you're dealing with larger input muxes. So maybe 2 transistors in series is okay for you. But what if you are implementing a 64:1 mux? Then it makes more sense to go with one implementation like this instead of having 6 transistors in series. Again, depends on the delay that you are trying to optimize. If you're trying to optimize the delay from the selection signal to the output, right, versus trying to optimize the delay from the input to the output when the selection signal is already applied. So now this is a trade-off. You can see whether having a decoder here makes sense in that. If your input was already available, let's say halfway through, and one of your selection signal is changing, then maybe this is giving you a better delay. So you'll need some information about which delay you need to optimize before you start with this. So far, let me, yeah. It is improving the input to output delay for sure. Whether it is improving the selection signal to output delay, you'll have to work out and see how much delay your DC-VSL is taking, how well you have implemented it, etc. So then there is basically, you have to improve the decoder circuit itself. So you have to make sure that the delay from the selection signal to the output is minimum possible. So now how minimum you want it to be, based on that, you can choose the circuit that you want to implement it in. And given all the logic gates that we have gone through, DC-VSL and others, DC-VSL is right now a very good bet, right? Because it has the benefit of pseudo NMOS logic without it being ratioed or without having static power consumption. So we started with complementary static CMOS design style. Then we went to pseudo NMOS. Then as an extension of pseudo NMOS, we saw the differential cascade voltage switch logic based gates. Then we saw how to design certain circuits using pass transistors. And within pass transistor implementation, you can either implement it using transmission gates or you can use a restoring logic. So when you are starting a design, by default, your approach should be to use complementary static CMOS because it's very robust. At all points of time, your output is connected to either VDD or ground, right? Not at the same time, to only one of them at any time other than during the transients. It is ratio-less, which means it's very easy to obtain the correct functionality. You just need to place the transistors correctly and connect the inputs correctly. And it also doesn't have static power consumption. Yes. Yeah. Okay, good question. So the question is, if it is not coming from VDD or ground, it is probably coming from some driver. So let's assume that it is coming from an inverter. Right? And let us assume that we have one stage here. and it is driving some capacitance, right? Now this is also going to drive something, maybe another inverter. So now what is your question? Correct. Yeah. So let me assume another scenario like this. So let's say this node is being driven by two pass transistors. Right? So now if you have a, let's assume you have a rising edge here, corresponds to a falling edge, which comes here. Now this falling edge, through when this path is on, we know that this path is off, right? So you cannot have a current directly like this, right? But what can potentially happen is maybe the time taken for this path to turn off was slightly longer, such that this starts to propagate the signal here. But when it is propagating it here, you have two things that are trying to drive this node. One of these transistors, let's say PMOS, and you have the NMOS here driving this to ground. Through the switch, it is trying to drive this to ground. So now you have two things that are trying to drive the same node. Depending on which one is stronger, that will win out. But eventually, this is going to turn off. And once it turns out, even if there was a momentary glitch, your PMOS will be able to pull this back up. So you have a latch here. Something like this. If you have something like this directly connected to this node, then it is slightly problematic. You would typically have you'll typically have either an inverter driving this or an inverter at the output. It can potentially reset the value. It is more sensitive to noise in such case. So did you understand what he had asked? So in this particular case, you understood, right? It is okay because once this turns off, it is able to bring it back. But now let me replace it with a case like this. Right? Let's assume that the initial condition here was 0 and the initial condition here is 1. And they are driving each other back to back, right? This one is making it 0, etc. Now let's say you, because of the falling edge transition here, this one momentarily went down, right? So from VDD, you had a signal going down like this. Now, if it has gone down further, this going from VDD to a lower value can potentially reset the output here, right? So this can go from 0 to VDD. And this going from 0 to VDD will now again reinforce the transition from VDD to 0. Correct. So this inverter will have to be much, much stronger than the drive strength of this inverter. So it now depends on the relative drive strength, etc., etc. How long this is on. Yeah. But to be safe side, if you have a latch like this, which can potentially get affected by any changes happening in this node, I would isolate it from the next stage by adding an inverter. Any questions on this? Okay. All right. So now by default, the style that you choose should be complementary static CMOS because it is guaranteed to work for most of the constraints, right? But if you're working with very, very tight specifications, you need the delay to be very small, and you don't mind paying some penalty in terms of power or area, that is when you start looking at the other methods. So pseudo NMOS logic gates will give you lesser logical efforts, meaning you can have faster gates, especially for the pull down paths. But you pay a penalty in terms of the circuit being ratioed, which means you have to be very careful with the sizes to ensure that your output is a clear logic 0 or a clear logic 1. And you have static power consumption. Now from there, if you are willing to pay a penalty in terms of area, you can move to DC VSL. So you should be willing to pay a penalty in terms of area, and both the input and its complement should be available. Or you want both the output and its complement. Then it makes sense to move to DC VSL. So generally, we would use pseudo NMOS or DC VSL for construction of the NOR gate. because we saw that its logical effort was not increasing linearly. And pass transistors are especially very efficient for multiplexer implementations. So again, by default, stick to complementary static CMOS. And if you have some specific constraints, then you can consider using either of the logic gate implementations. So all of the combinational logic gate implementation styles we have seen so far falls under what is called as static CMOS. So these are all static CMOS designs, and static as opposed to dynamic circuits. So in static circuits, your output at all times is connected to one of the supplies, at least one of the supplies, and in some cases such as pseudo and MOS, to both the supplies. In dynamic circuits, we are okay with leaving the output node as a floating node, right? So we construct dynamic circuits based on two information that we have. The first part is a capacitor can have memory. You put a charge on a capacitor. Let's say I charge this capacitor to VDD. If there are no leakage currents, the capacitor is going to hold this VDD for a very long time, right? Now, in the presence of the leakage currents, this voltage will eventually leak and go down to zero. But at least there would be a reasonable time duration for which you can still say that the capacitor is at logic 1. So you rely on the capacitor having memory. Do you know what is the other point? What else do we rely on? How many of you have seen dynamic circuits before? So what else was specific about dynamic circuits that you did not see in a static CMOS style circuit? Correct. So what were you using for refreshing? What needs non-destructive? It shouldn't be. It shouldn't destroy the capacity. It shouldn't destroy the value stored in the capacity. Achha, reading. I'm hearing reading. Yeah, right. But something else, very basic. All your dynamic circuits were clocked, right? And the output was not available at all time instance. It was available only for a certain portion of the clock, right? So if you take any digital circuit, so you would have your digital circuit, and almost all digital circuits are typically clocked, right? So you will have a set of inputs going in, I1 to IN. So assume that this is a very big digital circuit with lot of combinational circuits, flops, sequential elements, etc. Given that this block is clocked, you would expect your output to be ready during certain phases of the clock, either at the rising edge of the clock or the falling edge of the clock. So given that you are already working with clocked systems and you expect your outputs to be ready during only certain portions of the clock period, why should we insist that our combinational circuit output has to be ready at all times, right? We make use of the fact that most systems are clocked. Therefore, we can have the output ready only for certain portions of that clock period. So this is the other idea that we make use of. Now we are going to develop a dynamic inverter based on a pseudo NMOS inverter. So let me first start by a pseudo NMOS inverter. This is connected to A, this is connected to ground. All that I do is I change this connection from ground and connect it to a clock signal. Okay, so we'll now analyze this, see what the problems are with this circuit, and then we'll try and improve on it. So let me draw the clock signal. Let me also draw the signal corresponding to A. Let's see what our output Y should be. When phi is equal to 0, what should be the value of Y? Phi is 0, A is 0. Therefore, this will be at VDD. correct? Now when phi is equal to 1, what happens to the output? So when phi is equal to 1, the pull-up path is off, right? A is equal to 0, therefore the pull-down path is also off. And if we neglect all leakage currents, it should mean that the output capacitor here is able to hold that value. So if this was VDD before, it will remain at VDD as long as phi is equal to 1, right? So I'm not drawing it with a solid line because it is not being driven by anything. It's just being held. It's a floating node. Now after this, at this instant, phi again goes down to 0. Therefore, it is being driven by the PMOS transistor. What happens now? Right, so you have the pull-up path on, pull-down path on. Let's assume that we have done a decent job of designing this, which would mean that it will come slightly lower from VDD and remain at some VOH value. Now what happens? So again, phi becomes 1, which means your PMOS is off. A is equal to 1, therefore your NMOS is on. Therefore, this will be able to discharge it all the way down to 0. So far, okay? Yeah, sorry. When the clock goes up again, it gets pulled to VOH. Right. So now what is happening is whenever phi is 0, your output is getting pulled to logic 1. Your capacitor is getting charged to VDD or to a value very close to VDD. So we call that phase as the pre-charge phase. So this is pre-charge phase. Right? And when phi is 1, you are evaluating whatever function you are implementing here. So we call that as the evaluate phase. So now let me ask you this quick question. Let us look at this region, right, where both the pull-up and pull-down paths are on. So that would mean that our circuit is now ratioed and you have a static power consumption during the state. I don't want to have static power consumption, right? Can you suggest a simple solution such that I can turn off my pull-down network when phi is equal to 1? Sorry, when phi is equal to 0. So add the inverse of the clock to the with the pull-down network. Okay, so let me add an NMOS here. So what should I connect here? Let's check if phi bar is the right answer. Right. So when phi is equal to 0 and this node is getting pre-charged, I want the pull down to be off. Right. So it has to be phi. So now with this correction, I can change the circuit as so it remains at VDD throughout and then it discharges. This is okay. So this is now a dynamic inverter for you. As a homework, why don't you implement a dynamic NAND 2 as well as NOR 2 gates? You can also size the 3 gates. So take a guess. We'll discuss it in the next class. Analyze how it should be. Yeah. So you'll have to start by sizing the inverter first, and then you can size the NAND 2 and NOR. So size all 3 gates and calculate both GU and G. Thank you.